Hello everyone. In this video, I'm going to derive the stiffness matrix of a bar element. What is a bar? It is a structure that is subjected to axial loading, but also keep that in mind. It is also a structure where one of the dimensions, that is the length, is highly pronounced compared to the other two dimensions, that is the breadth and the height. Such a structure is called as a bar. On the other hand, if the load is acting along the transverse direction, you have to call that structure as a beam. Now let me write the governing differential equation of a bar. It is AE into d square u over dx square plus q is equal to 0. This is the governing differential equation of a bar. If you don't know how to derive this governing differential equation, I highly recommend that you go back and watch my video on deriving this governing differential equation. That explicitly explains how we actually come up with this governing differential equation. Whenever you come across this word differential equation, always remember 3 points. Number one, everything in the universe is actually governed by differential equations. Almost everything in our universe. Number two, differential equations always have a secret inside it. It has a secret that is stashed inside it. So you have to turn the crack of mathematics. You have to use the power of mathematics to extract, to squeeze out that secret. Sometimes the secret can be displacement, it can be velocity, it can be temperature. In our case, the secret is displacement. Okay. Number three, not all the governing differential equations will have a solution. So we don't have solutions, exact solutions for all the governing differential equations. Sometimes it is a mathematical challenge. It is still a mathematical challenge to solve certain governing differential equations. So it is still an ongoing exploration. Okay, in our case, the secret that is stashed in is this guy, that is the displacement. Everything else is not a secret. Cross-sectional area, A is not a secret, so I can put a tick mark for that. Young's modulus, that's not a secret, you can put a tick mark for that. The loading, that's not a secret, you can put a tick mark for that. Now what I'm actually going to do is I'm going to write the weak form of this governing differential equation. Again, I have derived the weak form of this particular governing differential equation in a separate video. Please go back and watch that video to wrap your mind around the procedures. Mathematics is all about reviewing and revisiting the concepts. So constantly review and revisit the concept so that you are able to understand the equations to the point of automaticity. Okay, now the weak form equation of this particular governing differential equation is integral of AE into du cap over dx into dwi over dx into dx is equal to integral of wi into q into dx plus, open the bracket, it is AE into du cap over dx over the limit 0 to L, and it is over the limit 0 to L, and it is over the limit 0 to L. Now, what are the terms? That all the terms I think by this time you should be familiar with. Wi stands for the weighing function. A is the cross-sectional area. E is the Young's modulus. U is the displacement. And the Q is the rate of loading. So you are familiar with all these terms. And we have derived this particular weak form in a very, very methodical manner. Now, I'm going to apply this weak form technique to a small piece of a complicated bar. Now, I'm going to show you the structure of a complicated bar. This is what I call as a complicated bar. There you can see that it's definitely a complicated bar. You cannot solve this problem readily by using the techniques that you have learned from strength of materials. You cannot solve this problem readily. So it is a complicated situation. That's the reason why we have to use the technique of finite element method. Now what I'm actually going to do is I'm going to apply the weak form to a small piece of this bar. So what is the small piece that I'm going to consider? Maybe I'm going to consider a small piece here. Maybe this small piece, which I'm indicating by green color. Now what is the displacement corresponding to this small piece? You look at the displacement corresponding to this small piece. The displacement that is corresponding to the small piece can almost be represented by a straight line, which I will try my best to indicate by this red over here. There is a small discrepancy, but nonetheless, this displacement corresponding to this small piece can be represented by a straight line. So when you try to solve this weak form equation, the very first step is to assume a trial function. is to assume a suitable trial solution. So when you are assuming a suitable trial solution, the trial solution that you are actually going to assume is going to be a linear trial solution. So let me write that down. The very first step to solve this particular weak form equation is to assume a trial solution. And the type of trial solution that we are actually going to assume is a linear trial solution. And you have a very good reason for assuming a linear trial solution. I just told you that if you are taking a small piece, if you are localizing your attention on a small piece, then the displacement function corresponding to that small piece is a straight line. It is just a straight line. So the straight line equation is just going to be a naught plus a1x. Of course, you don't know the values of a naught and a1. It's what we are interested in finding out. So it can be a perfect straight line. The straight line equation is a naught plus a1x. So the trial solution that you are going to assume is going to be a linear trial solution, and that trial solution is u of x is equal to a naught plus a1x. So this is the first step. I think you are now familiar with the first step. You have understood the first step, so I'm putting a tick mark for that. The second step, step number 2, is to apply the boundary conditions. What are the boundary conditions that you are actually going to apply? So BCS, it stands for applying the boundary conditions. Now, if you look at this particular case, what are the boundary conditions? The boundary condition right over here, maybe I will switch colors, maybe I will use blue. The displacement right at this point is going to be u1. That's going to be one boundary condition, that is u1. It is the displacement right at the beginning of the small piece. Okay, and the displacement over here is going to be u2. So the displacement of that point is going to be u2. Since you are considering a small piece, if you are going to use local coordinates, so which means that if you're using a local coordinate, then if you reckon the length of the small element by using local coordinates, then this is going to be x is equal to 0, and this will be x is equal to L, where x is equal to 0, it is the local coordinate. So you see that the length of the element is being reckoned by using local coordinates, whereas this one is actually the global coordinate over here. Okay, so I have used local coordinates to reckon the length. So at x is equal to 0, the value of displacement is u1, and at x is equal to L, the value of displacement is u2. You may ask me this question, do we actually know the value of u1 and u2? No, we don't know the values of u1 and u2. So you may even ask me this question, how can you apply the boundary conditions if you don't know the values of u1 and u2? That is one of the greatest tricks that is pulled in mathematics here. We don't really know the values of u1 and u2, but still we will presume, we will assume as if we know the values of u1 and u2. We will turn the crank of mathematics. Finally, we are actually going to compute the values of u1 and u2. We need to find the values of u1 and u2 at the end. Because after finding the values of u1 and u2, once you know the values of displacements at each and every nodal points, you can find the strains, and then you can find the stresses. Once you know the values of stresses, you can take some smart engineering decisions. Okay, now the step number 2 is to apply the boundary conditions. So here we go. Let me apply the boundary conditions. At x is equal to 0, the value of displacement is going to be u1. So at x is equal to 0, the value of displacement is going to be u1. If you apply this boundary condition on the trial solution, the trial solution is u is equal to a naught plus a1x. If you apply this this particular boundary condition on this trial solution, you are actually going to get the value of a naught as u1, because at x is equal to 0, the second term vanishes and u becomes u1. So you are going to get the value of a naught as u1. Let me apply the second boundary condition. The second boundary condition is at x is equal to L, the value of displacement is u2. If you apply this particular boundary condition on this trial solution, u becomes u2 on the left hand side. A naught is already u1, which we have computed, plus a1 into L. Okay, I can now solve for the value of a1. a1 is equal to u2 minus u1 divided by L. So this is the value of a1. Step number 3 is I'm going to plug the values of a0 and a1 back in the trial function. So let me write that down. Step number 3, I'm going to substitute the value of a0 and A1 in the trial solution. TS stands for the trial solution. So if you substitute the values of A0 and A1 back in the trial solution, what is that you are actually going to get? U of x is equal to A0, which is U1, plus A1x. A1, the value is U2 minus U1 over L into x. If you rearrange this equation a little bit more smartly, that is, you take all the coefficients of U1 outside and take all the coefficients of U2 outside. If you just assemble that way, then the value of U of x is going to be 1 minus x over L into U1 plus x over L into U2. This is what you will be getting. Now, this is the first weighing function W1, and this is the second weighing function W2. You know, sometimes weighing functions W1, W2 are also called as the shape functions. In our case particularly, they are also called as shape functions, denoted by the notations N1 and N2. So U of x, now it is of the form N1 U1 plus N2 U2. Now let us go back and visit the weak form expression. In the weak form expression, you see Wi is there. I means I can take the values of 1, 2, 3, 4, so on and so forth. Now how many values I is going to take in our case? I is actually going to take only 2 values, because we have got only 2 weighing functions. We have got only 2 shape functions. So I is only going to take only 2 values here. Now our duty is put I is equal to 1 in this particular weak form expression and turn the crank of mathematics and see what is the expression that you are going to get. And then put I is equal to 2 in the weak form expression, turn the crank of mathematics and see what is the expression that you are going to get. So that's what I'm going to do that. So bear with me, I'm going to write the weak form expression once again, and I'm going to plug the values of I is equal to 1, and I'm going to put weighing function 1, that is the shape function 1, and I'm going to do the mathematics. So let me write that down, but let me write the weak form expression again. It is integral of AE into du over dx into dwi over dx into dx is equal to integral over the limit 0 to L, it is 0 to L over here, q into wi into dx plus AE into du cap over dx over the limit 0 to L. Well, I missed a cap over here. It means that you have assumed a trial solution over there. Now, what are the various things that are demanded in this weak form expression? Well, I need to know what is du over dx. Okay, let me find that out. Du over dx, if you differentiate this expression, you are actually going to get u2 minus u1 divided by L. That's the value of du over x. Okay. And what else is demanded in the weak form expression? Well, in the weak form expression, you need to know the value of dw1 over dx. So let me also find that down. dw1 over dx, if you differentiate the first weighing function with respect to x, you're going to get 1 by L. And what else is demanded? You also need to find dw2 over dx, because it is demanded in the weak form, and you are going to get 1 over L. If you differentiate this guy with respect to x, you are going to get 1 over L. Now, let me put I is equal to 1. So when you put I is equal to 1, this guy actually, let me use a highlighter here, this guy actually becomes dw1 over dx. Well, you have already computed what is du over dx, and you know what this guy becomes w1, because I is equal to 1, so wi becomes w1, and you have already computed what is this expression, and that expression is actually loading. But let me see. Okay, I think I missed a wi over here, but I have to write that down, so I'm sorry. So in the next step, it is, I'm going to put the values now. It is integral over the limit 0 to L. It is AE into, it is minus u1 plus u2 over L. I think that's the value of du over dx. And dw1 over dx is minus 1 by L into dx is equal to integral over the limit 0 to L q. And the first weighing function w1 is 1 minus x over L. Okay, it is L into dx plus, and the second value is wi into AE into du over dx. Okay, that's very simple. AE into strain is nothing but load. So if you look very carefully at that expression, you will understand that that is actually the expression for point load, or the limit 0 to L. Well, I have to plug the value of W1. W1 in our case is 1 minus x over L. Okay. Now I can bring all these terms outside and I can integrate with respect to x. Integral of dx is simply going to become x. When you substitute the value of limit, it simply becomes L. Okay, when you substitute the value of limits. So if you simplify, if you substitute the limits over there, the expression that you are actually going to get is AE into AE by L into u1 minus u2. This is what you are actually going to get if you simplify this, because these terms you can take outside of the integral. So you will be simply left out with integral of dx over the limit 0 to L, because these terms can be taken outside of the integral. And if you integrate this, you will simply be getting x, and the limit is 0 to L. So L squared is already in the denominator and L in the numerator, they cancel each other out. So you will be left out with AE over L, u1 minus u2. And what happens to the other term over there if you integrate and substitute the limits of this guy, or if you integrate and substitute the limit of this guy, you are actually going to get QL over 2. Okay, now how is that? Well, if you integrate the first term, it becomes L after substituting the limit, and the second term, it is x squared over 2. So it becomes L squared over 2, L in the numerator and 1L in the denominator. They cancel each other out. So it is simply L minus L over 2. That becomes L over 2. So it is Q into L over 2. So that is Q into L over 2. And what happens to this term if you substitute the limit? If you substitute the upper limit, it becomes 0. If you substitute the lower limit, it becomes minus P. The load at x is equal to 0. That's what you will be getting. Okay, because when you substitute the upper limit, this term completely vanishes. If you substitute the lower limit, you are going to get the load at x is equal to 0. Now I'm going to so this is going to be equation number 1. In a similar way, I'm going to put I is equal to 2 and I'm going to turn the crank of mathematics and I'm going to get equation number 2. So let me do that very quickly. When you put I is equal to 2, the expression is integral over the limit 0 to L, AE into du over dx is minus u1 plus u2 over L into dw2 over dx. What's the value of dw2 over dx? It is 1 over L. So I have to write 1 over L into dx is equal to integral over the limit 0 to L q into w2. What's the value of w2? It is 1 over L. Okay, w2, it's not 1 over L, it is x over L, I guess. It is x over L. That's the value of w2. You see from here, the value of w2 here is x over L. So into dx and plus, okay, it is w2, which is x over L, into the load. So I have written it directly. AE into du over dx is simply the load term over the limit 0 to L. Now in the next step, these terms can be taken outside the matrix. If you integrate that, that simply becomes L. So the term that you are going to get is AE into minus U AE over L into minus U1 plus U2, okay, is equal to, if you simplify this term, you are going to get QL over 2. And if you simplify this term, substitute the upper limit, you will be getting the load at x is equal to L. When you substitute the lower limit, it's just going to become 0. So this is going to be our equation number 2. All I have to do is I have to write the two equations in matrix form. You can write even one equation in matrix form. Just for example, I will tell you, you can write this equation, above equation in matrix form just like this: minus 1, 1, u1, u2. Okay, I think I have done that. You can write this as matrix form. This flower bracket indicates that it's a column matrix plus the load at x is equal to L. Okay, now, okay, that is equation number 2. Writing the two equation in matrix form in the next page gives you this matrix: AE over L, 1 minus 1 minus 1 1, u1 u2 is equal to QL over 2, QL over 2, okay, plus minus P naught PL. So this is the expression that you will be getting. Now, what is the physical meaning of this particular expression over here? Well, wait for that explanation, but this is called as the stiffness matrix. How do you say this is the stiffness matrix? You see this term over here, that is stiffness expression. Okay, A by L is the expression for stiffness, so we call that as a stiffness matrix. Does each and every term in the stiffness matrix, once you get it inside the matrix, will it have a meaning? Yes, it definitely has a meaning. And what about this matrix? It is called as the displacement matrix, simply denoted as U. What about this matrix? It is the force matrix due to UDL. What is UDL standing for? UDL stands for uniformly distributed load. And what about this matrix? It is the force matrix due to point load. Okay, due to point load. That negative sign indicates that it's a reaction load, this guy over here. But what is the physical meaning of this matrix? How is that we are going to assemble the matrix? If a little consideration will tell you that if you are considering a small, where is that complicated bar that we have drawn? Okay, over here. So for this particular case, we have got this expression A by L, 1 minus 1 minus 1, 1, U1, U2, followed by the load, that is QL over 2, QL over 2, plus the force due to the point load minus P naught PL. Now you can get exactly the same by considering another small piece, and then 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 another small piece. So what you will be getting, a matrix is being generated for each and every small piece, and you have to solve all these matrices simultaneously to get the values of displacements U1, U2, U3, U4, U5, U6, and U7. So how do you solve them simultaneously? How do you assemble those matrices? And what is the physical meaning? And what is the procedure to assemble them? In the next video, we are exactly going to do that. Thank you all for your patience.